given the output of my classifier. Okay, so it's fairly independent from your classification problem, and you can train your sigmoid layer with only 2 parameters. And so, how to go about the training is basically what the whole paper is about. But the idea is that one. So they provide the algorithm at the end, which is quite neat. It's not something people do anymore. But so what are the peculiarities of the algorithm? So the first one is that you are also minimizing a log likelihood. So you define it just like that. That is just the fast way for binary classification to calculate that function. And you're fitting those 2 parameters A and B. So the first question is, how do you choose the training set? And their answer is actually a clever one. So they propose a trivial answer, which is use a holdout calibration set. So split between 70% training, and then you have a 30% holdout calibration set. But then they propose a more interesting one, which is using cross-validation. And cross-validation is simply instead of dividing your set in 2, divide it in k. They propose k equals 3. I think I can erase this. So divide your training set in three different sets. What you do is you train your, well, in their case, the support vector machine, but in our case, your deep model. You train it on 2 of them and test on the other one, and that gives you a number of predictions. Okay? Then you do all the permutations, so you train on these, test on that one, and that gives you F1. And then you train on that too, and test on that one, and that gives you F2. So it's a training set. So each of these sets is produced with a different model, because each model is trained with a different training set. But if you take the union of all these sets, you have your calibration set. And this calibration set is way richer than any of these individually, and it is much larger than just 30% of your training set. It is actually the size of your training set. Okay? Is that clear? Cool. So that is an interesting way of presenting your training problem. So that is step 1. You have your training set, and the second step is regularization. So of course you are fitting 2 parameters. And if your labels are very well defined, you have a very big chance for overfitting. So they propose a very funny regularization term, which means that they basically say we're not going to put any additional regularization term, but rather we're going to say that our targets are not absolute targets. Okay? So instead of saying, okay, when you're telling me for an example, and let's use the 3-class example, 0, 1, 0, and you're trying to calibrate for this class. Oh, sorry. So let's say you're trying to calibrate for that class, and if you remember the loss function, so our loss function is the negative log likelihood. Now it's going to be of F. And you have Y and F. So if you're doing it for a single one, let's call it Li of Yi. That's going to be the sum over all the examples of minus log. So Yi log F. Yeah. So that Yi, instead of saying, okay, there's a 100% chance of that class being right, the regularization term says, okay, it is never possible to have a 100% probability of a class. So instead, let's limit it using prior knowledge about the data. Okay. So what the algorithm does is, well, you say, well, your t for the positive class is now not going to be 1, but it's going to be 1 minus an epsilon plus, so epsilon plus. And if it's the other term where this is 0 and you are actually predicting 0, well, there's actually not 0 probability ever, so that's going to say there's a Tn minus equals epsilon minus. Okay? And so there are a bunch of things that probably Arvid can explain better about why this works, but it has to do with not pushing the examples to the margins. It's about making sure that the loss function doesn't make your boundary too hard, so that you don't overfit your data and don't come up with a sigmoid that tells you 100% all the time. Okay? And then you only have 2 terms to fit. You have to fit A and B. And your priors are given by the number of examples, so your Tn plus is given by the number of examples that you have in your data that are of the positive class, and then the T minus is given by the number of examples in your data that are of the negative class. Okay, so that is the algorithm. They kindly provide an optimizer for you. So if you want to implement it yourselves, it's down here. The results are actually quite interesting. I think that one of the interesting things about this paper is that they actually make a statistical analysis of the results, since they do cross-validation. And what do they show? Well, they show that first, for most of the cases, there is not that big a difference in the number of errors that the support vector machine plus sigmoid makes against a raw support vector machine, which is good because we don't want to compromise the accuracy of our classifier. But they also show that this probability actually looks more like a probability than the raw support vector machine. Than the raw support vector machine. So if you want to use a regularized likelihood, it's not as close to an actual probability distribution. And the other thing they propose is that, well, after you have your A and B parameters set, you can retrain your model again. So those A and B already know how the data looks like, so you can retrain your support vector machine to boost accuracy again. They didn't do it here, and all these experiments are done using cross-validation, but it is something that they propose. So what does that look like in our little toy example? So I wrote the algorithms here step by step. If you guys want to double check it, please do. And of course, there's a lot of optimization done here. I tried, but I didn't have enough time to test it properly to make it in Keras. So to do the trainable sigmoid layer, I couldn't get it to work, but if you guys can go in there and find out why it's not working, please do it, and then we can have a Platt scaling layer or whatever, and we can push it to TensorFlow, maybe make a contribution. But anyway, those 2 things don't work at the moment. You can modify the algorithm to work in the multi-class